At IB standard level chemistry, you have to be comfortable with the idea that halogenoalkanes, in other words alkanes that have got a halogen like chlorine or bromine attached to one of the carbons, can undergo a process called nucleophilic substitution. In other words, that the chlorine is substituted with a nucleophile, the nucleophile being something that's attracted to that positive charge. The nucleophile is acting as a Lewis base and has a lone pair that's attacking that delta positive carbon that's there. Okay, so it's going to form a bond. This pair of electrons becomes a bond between the oxygen and that carbon. It becomes a covalent bond. Now carbons can only make 4 bonds, and so this bond here between the carbon and chlorine is broken in a process called heterolytic fission, which is where you're breaking a bond where both of the electrons go to one of the 2 atoms. And what we end up with is, in this case, ethanol and the chloride ion. It might be you've used sodium hydroxide here, in which case you'd end up with sodium chloride, but really it's the hydroxide doing the work and the chloride is the thing that's produced. The sodium really is a spectator ion, it's not doing anything. At high level IB level, we have to be aware that there's 2 kind of versions of this nucleophilic substitution. There's SN1, which is substitution nucleophilic 1, and the 1 is telling you that it's unimolecular. In other words, there's one reactant in the rate determining step, and so the rate equation, the rate is equal to K times the halogenoalkane. And that's it for the rate equation, is just that thing. Therefore, the slow step only involves the reactant halogenoalkane. So that mechanism involves the halogenoalkane breaking apart that bond, that polar bond between the carbon and the chlorine, breaking. Now this mechanism, tertiary halogenoalkanes will undergo every time. I'm going to draw this a little bit more simply now. I'm going to draw the CH3s just simply like CH3, and we end up with a carbocation intermediate, and that word we have to know, carbocation. And that's a mechanism, that's a mechanistic step we have to be aware of, and of course you'll generate the chloride ion. Don't forget to draw that if you're doing this in an assessment. Now, tertiary halogenoalkanes undergo this mechanism because the product that forms is somewhat stable, stabilized by the fact that you've got 3 alkyl groups around it. Now, the explanation for why it's stable is there's going to be different things you read in textbooks and what you might read and see on videos. A perfectly acceptable answer at IB though is there's a positive inductive effect from these alkyl groups. In other words, they push electron density towards the carbocation, the carbon at the center there, making that cation more stable than it might otherwise be if it was, say, a primary carbocation. Right. So then the hydroxide comes along in the second step and attacks that carbon to make sure this arrow starts in the center of that carbon-chlorine bond, because it's showing the movement of a pair, hence the double-headed arrow of electrons, and to make sure this arrow starts either at the lone pair, ideally at the lone pair on the oxygen, which I've drawn really badly now, or it'll be okay if you draw it from the minus for IB level. That's showing the formation of a carbon-oxygen bond. By that pair of electrons becomes that covalent bond, and we end up with the product tertiary alcohol, which would be this. That reaction is quite fast typically because the carbocation forms is somewhat stable. The energy profile diagram for that will be in 2 stages. We've got the first stage with the bigger activation energy to form the intermediate. There's reactants, that's energy on that scale, and the products are down there, and the intermediate is that well there in the middle. Oops, that's my products. So reactants, intermediate products. There's an initial activation energy and a second activation energy. That's usually lower than the first. Right? If this mechanism happens with a secondary halogenoalkane, which it can, and that secondary halogenoalkane is chiral, such as this molecule here, such as this halogenoalkane here, then the product, if this was chiral, I should have drawn this 3D really. So I'm going to draw it again 3D. Yeah, it's not the best picture, but this is meant to be a 3D representation of this chiral halogenoalkane. It's got a chiral carbon because there's 4 different groups coming off it. If this is a single enantiomer and it undergoes then an SN1 mechanism, which it can under the right conditions, then the product you get will be, again, the alcohol. This time it's a secondary alcohol, but we have no longer got retention of that stereochemistry. We've got scrambling of the stereochemistry. So in other words, it's no longer it's still a chiral carbon, but it's not a single enantiomer. It's a mixture, 50-50 mixture of enantiomers, which we call racemic. And that comes from the fact that, just look at it here, up here, that this thing is sp3 hybridized. There's 4 different groups coming off it. It's a tetrahedral carbon, and it can be a chiral carbon if there's 4 different groups coming off it. But the intermediate carbocation that forms is now sp2 hybridized. It's flat, it's planar, trigonal planar, and the hydroxide that attacks it can attack equally from either side. Think of it a bit like something like a hand that's flat. The hydroxide can attack that carbocation from either side, making the molecule that's formed racemic. Primary halogenoalkanes, though, will always undergo SN2 version of the mechanism, where the rate equation is rate is equal to the rate constant multiplied by the halogenoalkane again, and multiplied by the hydroxide as well, which means the hydroxide and the halogenoalkane are both involved in the rate determining step. And so the rate determining step must be the first one. I'll just go back to the previous page to highlight that this was the rate determining step in the first mechanism. It's a 2-step process. This is a 1-step process where it essentially goes from there to there in a concerted mechanism, whereby the carbon-oxygen bond is formed and the carbon-chlorine bond is broken all at the same time. So rather than being stepwise as a concerted mechanism, all happens at the same time. That's what concerted means. We end up with the product like that. But it's worth realizing that we can draw an intermediate here, where this is the carbon that's changing. This is the carbon that's being attacked by the nucleophile. And the 3 things coming off that carbon that don't change are that carbon, the CH3, this hydrogen, and the other hydrogen. So we can draw those like so. Imagine they're kind of flat, again, like my hand, kind of trigonal planar. We can show the bond that's forming between the between the oxygen of the nucleophile and the carbon. We draw that as long and incomplete. And at the same time, that carbon-chlorine bond is breaking. So that's not an intermediate, that's not something that exists for any length of time, it's not something we can actually detect, but we know it forms. And this is the sort of part way along the mechanism. So this is what we call the transition state. And if you were to draw an energy profile diagram, your normal exothermic energy profile diagram with reactants and products, energy like so, the transition state is at that point there, the point at which the carbon-chlorine bond is being broken and the new carbon-oxygen bond is being formed. And again, if you've got a secondary, the primary always undergoes that mechanism, but if you've got a secondary halogenoalkane, I'll use the same one as before, and it undergoes SN2 mechanism rather than SN1, then we get a different situation. I'll draw that and discuss it. Now, if you've got a secondary halogenoalkane with a chiral carbon, and it's a single enantiomer, so I've drawn it 3D here, so make sure you can draw molecules in 3D. If that is attacked by hydroxide, and it undergoes the SN2 mechanism, the 1-step concerted mechanism, where the carbon-oxygen bond forms at the same time as the carbon-chlorine bond is being broken, you end up getting inversion of stereochemistry, right? So the way that we draw that, the easiest way to draw it, I think, is replace the chlorine with the hydroxyl, the OH, and then draw one of the groups in exactly the same place. I've drawn the ethyl group CH2, CH3 in the same place, but I've switched the other two groups. Still got the thick coloured in bond there and the dashed one going behind, but I've switched the position of the CH3 and the H to show inversion of stereochemistry. That happens because if you look at the transition state here, as the hydroxide is coming in and attacking the carbon, it's probably better if you look at, as the hydroxide is coming in and attacking this carbon, the molecule, the stereochemistry flips like an umbrella inverting to form the new product. There's some lovely animations of this, and then a longer version of this video where I was teaching it. You can see some models that I was using to describe it too. So in summary then, SN1 is a two-step mechanism with which always happens with tertiary halogenoalkanes, and you get scrambling of stereochemistry, whereas SN2 that I've just finished with here is a one-step concerted mechanism where you get an intermediate form and you get inversion of stereochemistry if you've got a chiral halogenoalkane and reacting with a hydroxide. Hope that's useful. Learn those mechanisms, you're going to need them.